Hi, thank you everybody for coming. This is the power of intelligent flows, doing real-time IoT botnet classification with Apache NiFi. As you can see up here and on another slide, we reference the two blokes in front of you. I left Andre's name on here because one, he did a lot of the work, two, out of respect, he's not dead, he's just not able to be here today, so he's doing fine. Again, we'll go over kind of a brief prologue to the scenario that we encountered and the problem that we were trying to solve. Talk about how logs were the solution that we decided to use, what the challenge was in actually identifying the classification of the botnet systems, our solution, and then wrap it up a little bit. So I am Andy Lopresto. I work for Hortonworks. I am a PMC member and committer on Apache NiFi that extends to the subproject NiFi MiNiFi. Previously worked at Apple, Tiger Text, did a lot of device firmware and financial security work. Andre has spent a lot of time working in cybersecurity, and he particularly likes logs and doing forensic analysis and digital incident response. He is also a NiFi PMC member. So a little bit of background. This is the botnet kill chain and the Honeypot. Now the kill chain is a term derived from obviously military usage, but has been used extensively in digital forensics and attack response. And so you can see the 7 segments here. What we're really going to focus on are the 3 in the middle, the delivery, exploitation, and installation. And that's when an attacker is trying to get their, sorry, everybody familiar with a botnet? Okay. You have a collection of devices that have internet connectivity, and they have some prescribed purpose. Could be computers, phones, could be connected cars, could be Samsung connected refrigerators, not to give any brand awareness, but that was an example that happened in reality. So all these internet connected devices have a CPU, have some kind of network connection, and they have a job to do. Frequently, they have low, minimal, or no security, and so the list of who can tell them what job to do expands very rapidly from the developers and manufacturers and users into anybody who has an internet connection. So a botnet is a collection of these devices that have been compromised and converted into a bot, and then are now mindless zombies calling out to some external command and control system, performing some kind of activity. I think the activity of today would be cryptocurrency mining. It used to be denial of service attacks against PlayStation if it was Christmas, like all kinds of ridiculous activities that refrigerators shouldn't be doing no matter what, instructed by whoever has designed or is in current command of the botnet. So the delivery, exploitation, and installation phases of this kill chain are when the botnet developer is trying to spread the bot to external systems, get it installed on those systems, and get it to be persistent on those systems. And that's actually what I just talked about. So Andre and I decided to set up a demo environment, and this was based on Amazon S3. We built these EC2 instances, and Cowrie is a honeypot tool for SSH and Telnet. So it allows external users or services to try and communicate over SSH Telnet, and essentially just records everything that they're doing and replies back with some pretty standard output that lets them think that they're actually accessing your system. On each of these little EC2 instances, we also put an instance of Apache NiFi MiNiFi, which is our edge agent. It brings all the key features of NiFi out closer to the edge, closer to the data collection points of your ecosystem. So it lets you get things into having data provenance earlier, being able to filter, transform, route, encrypt, protect, prioritize all of this data much earlier in your collection scheme. We had a central EC2 instance, which was running at the time NiFi 1.3.0 with security enabled. So that meant that all the communication between our MiNiFi instances and our NiFi instance was using security, it was using TLS, mutual authentication, so client certificate on each end, doing all that verification. And it meant that, you know, one of the dangers of going and looking for bad guys is that you will find bad guys, and they don't get very happy when you start messing with them. So we really wanted to make sure that whatever we were doing and collecting this information, we didn't expose ourselves to something worse following on. So this is kind of where my experience comes to the forefront. When we were building the flow, right? Who has used NiFi before? OK. NiFi provides a graphic user interface, which is backed by a REST API, but it allows you to build data flows. And the flows they consist of a number of processors, which are these black box components, accept some form of data in or generate their own data, and then output or in other ways terminate the data. So a lot of them do transformations, routing, ingest, exfil. When you're building a flow, there's a tendency to approach that with a very prescriptive method and go, I want a flow that is 4 or 5 processors long, and it goes A to B to C to D to E. And that can work. There are scenarios where that is the right approach. When you're approaching a new problem, or you're approaching a problem that you don't have a specific idea of how to tackle, our recommendation is not to try and be prescriptive. Don't start at the beginning and go, all right, well, I'm going to use this processor, and then I'm going to follow on with this, and then I'm going to follow on with this. Start at the end, like you're solving a maze. You know where you want to get. You know what format you want the output to be. You know what destination you want it to reach. You know how quickly or how slowly you want it to be there. And start there. And NiFi makes that very easy because you can drop a generate flow file processor in at any point of the flow and generate whatever the data needs to look like one step prior to where you are now. So start at the end and build backward. And you know that when you get to the beginning, everything in the chain that follows on is working already. So logs. This is where Andre comes in. Andre really loves logs. So what we did was we put these MiNiFi instances, we built a flow in the NiFi instance, right? Nice graphic user interface, good flow design system. And we built a flow that tailed the log file that was being written to by Cowrie. And Cowrie is really nice in this regard, and I think there's a slide in the next one, but shows the log output of Cowrie. It's extremely useful because it's both human consumable and machine consumable. And that just means it's in nicely formatted JSON, right? So I, as a user, can look at the log and immediately understand what's happening, but I can also send that to a machine system and have it parse that without having to do a lot of transformations or CSV breakouts or things like that. Now, from each MiNiFi instance, we push to an Amazon S3 bucket. And we did that really just to demonstrate the versatility here, that it's not something that's dependent on NiFi. We easily could have done this using the site-to-site protocol and gone MiNiFi to NiFi directly. But by using S3, we were saying, you don't have to have MiNiFi out at the edge. You could have these Honeypot instances that are running something that's a completely different stack, nothing that we control. Push using S3, maybe you write a command line interface to do that. Whatever it is, get the data into a shared resource in a standard format, and NiFi can pick it up and go from 0. If you didn't have it in JSON, if you had it in some kind of CSV, you could easily have NiFi pull that in and transform it into JSON and parse that out as well. So there's a lot of versatility here. There's no lock-in, and these systems are very loosely coupled. They don't, if you make a small change on one, it's easy to make a corresponding change on the other, but there are a lot of changes you can make that only affect that specific system and don't require a corresponding change. So we'll talk about what actual data we brought in. The Cowrie logs include username and password. They include the command that the attacker tried to execute and the parameters of the command. So a lot of times it's trying to cat different proc or mount paths. It's trying to execute a shell and call out to some IRC server. And like I said, these are all JSON entries. Cowrie formats them very nicely. They're single line. They're easy to parse. And we have some NiFi processors that are out of the box, perfect matches for these, split text and evaluate JSON path. Now, split text was to split these into individual flow files, and that's because some of the custom processors that we wrote depended on each flow file having one log entry in it. With the newer versions of NiFi, the record processors could really add to the performance here, but we needed to rewrite the custom processors that were using an external service in order to consume it in that format. So this is a log example, and you can see that it starts with event ID, and it's either an input or a success, right? It's what the attacker is typing in, or it's what we're responding to the attacker. There's also a couple session connect and close and a login. But for the most part, it's command input or command success. You have a timestamp, obviously nicely parsable. And then you have the message. And so if you look at, you can't see my cursor, but let's just look at the bottom one. The message was command bin busybox echo E and then some hex code there. But you can see that that's what the attacker's trying to put in. They're trying to echo some Unicode output into a file and then semicolon, there's more on there. So they're trying to inject some data into the target system and then have it run something on that system. So this is the flow that was just to ingest those log files. You can see that the first one is a list S3, so it's calling out to the Amazon S3 bucket and retrieving a list of all of the entries that are in the bucket, the objects that are in the bucket, and then a fetch S3 object, which will receive a flow file for each object and go and retrieve it. Then you have a split text, which, like I said, is breaking those large log files into individual flow files, each one with one specific entry, followed by evaluate JSON path. And what that's doing is ensuring that what we can pull out of that, like if something was poorly formed or malformed, we want to send that off to an invalid log destination. And then we could manually inspect that. We could see if maybe we deployed Cowrie and we messed something up on the setting. But for the most part, we're going to bring in the successes into a do something with logs process group. So the challenge. Anybody familiar with this picture? It's blind men describing an elephant. All right. Now, I happen to work at Hortonworks. Elephants happen to be a big part of our job. But this is actually, I think, a really good example. Each one of the people in the photo, or in the picture, is describing the entire state of the system based on one small piece of data that they can understand. And so, obviously, none of them are able to describe the entire state of the system accurately because they don't have all the data, and they're hyper-focusing on the one thing that they have access to. So why is that relevant to this topic that does not have to do with elephants? Logs in isolation will rarely ever provide a complete view over what's happening. And especially today, everybody here is familiar with big data. The absolute scale of information that's available is sometimes terrifying. That is a product of the capability to capture more than ever before, but it's also a product of the verbosity of what we output because, well, storage is cheap, network is cheap, so we can just write out everything now. We don't have to be considerate with what we're outputting and evaluate at design time whether or not this is important in context. That's more of a critique of developers than it is of the systems, but the systems enable the behavior, and the behavior is going to continue. So how can we try to understand what's happening given that absolute deluge of data? And finally, these bots use semi-random values to try to avoid pattern matching and easy analysis, right? If we can just write a rule that says anything that starts with XYZ, filter out, they're going to start introducing random variables, random input to try and make that more difficult to match. So what's our solution? We'll treat the logs as data, right? We tend to go through and try and trace activity through the logs and look at logs as behavioral patterns. But you can also look at individual log entries as discrete units of data and separate those out. And then essentially, this is not an ML talk. This is not a AI talk. But we were training a model by gathering all this data, trying to break it down into what's important, what's not, and then develop some behavior as feedback to that. So if you look at the specific log entries here, you can see we have the event ID, timestamp, message, system. We can break those pieces out and start to see, look at the third line in each highlighted box where you have command found, /bin, busybox, and then 5 random ASCII characters. That's the bot trying to introduce random things so that we can't just say block anything that's bin, busybox, and then a specific path. So we looked at that and said, okay, introducing semi-random values to try to avoid detection is not a new problem. That's happened before, and we've all experienced that with spam. And there are really good solutions. I won't say that it eliminates spam, but that certainly, I mean, if you have a Gmail account, when was the last time you got one of those emails in your actual inbox? Everything's caught because these little patterns, even if it's not byte for byte exact, it follows the same family of pattern. And Bayesian and spam analysis and all kinds of stuff, there are existing solutions that tackle this problem. So how can we adapt those to the botnet identification and classification problem? Well, there's a tool called locality-sensitive hashing. Anybody familiar with cryptographic hashing? I say MD5 in quotes because it's not, but MD5, SHA-1, SHA-256, things like that, KICKAC. Cryptographic hashes are built so that a very, very small change, even 1 bit changing on the input, will drastically change the output of the hash algorithm. It employs something called the avalanche effect to try and change about 50% of the output based on that change. So with your cryptographic hashes, if I have an image and I change 1 pixel in the image, the hash output of that same image will be completely different from the original. Locality-sensitive hashing is kind of the opposite. It's an application where we want to be able to group things that are similar but not identical closely together. So if a small bit changes in the input, only a small output change will occur. And as a ratio, we can kind of gather up how similar two things are by how much of the output on the hashing is different. These are used in a number of places. Like I mentioned, anti-spam, but also near duplicate detection. So for a lot of image detection and things like that. In genomic study, they're also really important because that's a huge amount of data. There are things that are very similar but not identical because these are natural organic systems. And so using things like LSH to closely group things that are similar is really important there. So this is our complete flow, and it's really blown out on the screen. You can see the logs are coming in. They're being merged to collect them into a single flow file that has a bunch of log entries. The Jolt transform JSON, it just puts it into a format that was easier to work with, but it can do that on large groups of logs in a flow file at once, so we don't need to have them split in order to do that. And then it goes to route on attribute. So we pull out things that are matching a port scan pattern, and we put it into one process group, because we know what to do with port scans. We take things that don't match, and then now on the second column, we're going up from the bottom. So generate ssdeep hash. ssdeep is a specific implementation of locality-sensitive hashing. TLS hash is another. So first, we generate the ssdeep hash, and we compare what we're getting to known ssdeep hash values that we've previously generated by running this flow. So the first time the flow runs, on the very first input we get, we have no seed data, and that's fine. We'll build up some very untrained seed data and store it locally. And the next time we run this, or the next time we get data in, it's now comparing against the seed data that we'd built originally. Now, if it succeeds and it matches, you see it shoot off to the right to the matched samples block. If it doesn't, then we do the TLS hash. And it's the same process as it was with ssdeep. It's just two different options to try and perform the same activity. Again, we compare the TLS hash. If it's not found, so now we've gone through two different hash algorithms. We haven't been able to find anything that looks like this. So we send it out to another process group and say unknown samples, so stuff to evaluate. But we have had two relationships that go to the matched samples. So anything in there is something that we've encountered something similar to this before. Yeah. Are there questions on the flow here? Are there questions on locality-sensitive hashing or any of the components that go into it? Yeah. Yeah. Yeah, and actually, that's a good point. Everything that's here, all the code and the flows are open source and available on a GitHub repository. So the link's at the end. So if anybody wants to try and recreate this, science is verifiable. Please take our examples and run it yourself and see what results you get. Okay. Oh, yes. In this case, it was running on EC2 instance. Sorry, the question was, you might have millions of lines or billions of lines in the log entries, and your flow file might take gigabytes, and is this going to affect the NiFi processing? This was running on an EC2 instance. I think it was a medium instance. We didn't see any kind of problems. We only had, I think it was 4 or 5 Honeypot nodes deployed. So if you had thousands deployed, you'd be getting much higher volume of data, and you'd want to put this onto either a larger box or a cluster to distribute some of that load. But for the most part, I mean, we never saw any issues with volume being an issue. Yeah, and also if you move this to the convert record, to the execute record processors, it'd be even faster because you wouldn't have to do the split and recombination. So, yes.
So depending on who we talk to, some people say we should use NiFi only for telemetry, or like here for more complex stuff.
Who said don't use NiFi? No, I'm just kidding. So NiFi is a data flow tool, and the stated goal and the design objective of NiFi is to move data from distributed, disparate sources into wherever you need it to be. That could be a large Hadoop cluster for analytics and processing. That could be simply another FTP server somewhere. There's a great variety in the destinations. If you have complex event processing, NiFi is not the best tool for that job. Spark ML, Spark Streaming, there's a number of different tools, Python notebooks, whatever you need to do. In this case, one, this is a contrived example because we wanted to do a demo of NiFi in a presentation. So we weren't going to say, NiFi is 8% of this demo, the rest of it's somewhere else. I'm not getting invited to do a demo if I do that. But as far as doing simple event processing, you can do that in NiFi. And in this case, we didn't have any performance issues. We weren't slowing down somebody else's enterprise system. We weren't competing for resources on a shared cluster. There was really no downside to doing this. If you're in an enterprise environment where you have multi-tenant authorization, shared instances, and you have resource competition, then yeah, you might want to offload it onto a Spark system or offload it write it to HDFS or HBase or something, have a different process, read from that and perform modeling or training, and then write it back to another destination, and then NiFi can pick it up again and route it somewhere else. So it really depends on the use case that you have. As far as only use NiFi for telemetry, I don't know if I subscribe to that, but there's a variety of things you can do with NiFi that it's not the best tool for, but it supports. There are also things that NiFi is the best tool to do. So, any other questions? Yeah. No. Yeah. So, yes. So compare hash is essentially using, in either case, TLSH or SSDeep. It's doing a hash comparison. But again, imagine the hash is 64 bytes. It's essentially, I don't have this running right now, so I can't show you the configuration, but it's very simple. You're literally just setting a fractional value to say what % similarity is it. So in this case, you see matched samples and not found are the two output relationships, as well as failure. There really wasn't anything that failed. So for matched samples, it was if the similarity score is above, I think 0.8 is what we set. And in not found it's below 0.8. So anything that the generated hash was more than 80% similar to a known hash was sent to the matched samples. Anything where it was less than that was sent to not found. As far as the actual comparison, it's just lexicographical comparison of two strings.
And how are you holding that? All the ones that you've seen before.
So in this case, so everything that's bright green was a custom processor that was written for this. It's just storing locally in like a hash map and reading. I mean, these were small. We got really good results even over, I think it was like 20 known hashes for each.
That could easily be a Redis.
Could be Redis, could be a database. If it was using the records, I would say use a lookup record processor. There's plenty of ways to enrich. So in NiFi, I kind of think of it as like you have a linear flow, not completely, but just in this little case, you have a linear flow where your actual data is flowing through, and you have kind of like a T-junction where some other data is coming in. It's not two equal sources of data that are being merged. It's your actual data that's under examination, and then some kind of enrichment. Usually the example is like geo-enrichment. Like you have IPs coming in, and you're adding latitude and longitude or something like that. Or you have some kind of key coming in, and you want to do a lookup into some kind of either hash map, Redis, whatever distributed cache map, and just pull some additional enrichment information and add it in without slowing down the flow of the data. So yeah, I mean, in this case, like I said, it was just local, but you could easily pull it from anywhere. Okay. So wrapping up, the key takeaways, I would say, treat everything as data. Don't get hung up on whether or not the producer of that output expects it to be data, right? It's very easy to use metadata as data within NiFi. And one of the best ways to demonstrate that is that NiFi itself really supports that philosophy. If anybody has used it and you see the provenance data, right? All the historical lineage of changes that go on with the data that's actually in your flow. For some people, you export it to Atlas and you examine it that way. For other people, you look at it when you're debugging a flow. Some people never look at it. You can take all that provenance data and use the site-to-site provenance reporting task and export that data. And you can actually hook that reporting task up to the same instance of NiFi and just send it into an input port. And then feed that into a flow. Do whatever you want with it. Transform it into JSON, feed it into a machine learning algorithm, train a model. So I had an intern a couple years ago who actually took provenance data and used it to train a model using k-nearest neighbor algorithm, and then was able to look at flows and start to detect when a flow was brittle or suggest that you remove a processor because it wasn't really needed, it wasn't in the long pole of the path. And you could extrapolate that into actual examining data that's coming in, looking at hardware, early field failure detection, things like that. So there's a wealth of data that's in the provenance that many people don't take advantage of. And the easiest way to do that is to feed it back into NiFi and let NiFi manage it the same way you let NiFi manage any other data that you're ingesting. Being flexible on how you build the data flows, that's obviously, like I said earlier, there are times where it's good to be prescriptive. There are times where you want to build it out from the back and say, I know where I want to end up. Let me see the ways that I can get there. Apparently unrelated domains may speed up your results. In this case, it was, we see this semi-random value being injected to try to avoid pattern detection. Has that already been solved? Yes, in spam identification. Andre's really excited about MiNiFi. So aggregating data at the edge whenever possible. Like I said, we could have easily used any number of tools or written a Python script or just done something on the command line to push the log files up to an S3 bucket. But using MiNiFi wasn't, this is a little while ago. Using MiNiFi was a good example of a newer tool and being able to integrate that, not just with NiFi, but with a variety of ecosystems, like just pure S3, so that it's decoupled from your central data collection system. He added that last part. I disagree. All right. Other applications for this. We could, in this case, we're using this to classify the botnets and understand what's happening, but we're not taking any action based on that. We could start automating IP blocking or firewall rules. We could update the signature definition list. So you were asking, where is it reading from? We were just putting it into the local file and reading back, but we could start building that up, putting metadata on that so we see how many hits we're getting on a specific signature. And maybe if we're getting 1,000 hits on one and maybe 10 on another, we want to increase the similarity score to that one that's more popular. Because maybe it's accidentally popular. Maybe it's something that's innocuous, but it's getting caught and compared to everything, and it just happens to have a similar spam score. So based on that learning, we can start to refine the model and be a little bit more specific. This could also be used, I use epidemiology here, but not in a medical concept, but in a spread of the actual botnet. Like when you have these LSH scores, you could start to trace them and model how the botnet is actually spreading itself and what vectors it's using. So if you see that the same commands are happening on these Cowrie logs as on some industrial control system or a SCADA system, you can start to see where it's actually taking foot and how it's getting that foothold and spreading out to other systems. As well, because these are the similarity, or because of the similarity between these LSH values, you can start to see if a specific family of malware starts to have the same activities as another. They might be related, They could be completely unrelated technically, but the author of one learned from or used to work with the author of another. You can start to create these loose associations just based on the similarity scores, and then kind of focus your more expensive investigation into what's going to pay off most likely. Could also be used to support attribution of the malware samples. This is where it gets really tricky because attribution is always dangerous. There's essentially just a confidence level, and for different use cases, that confidence level needs to be at different levels. But you could start to build essentially a case for specific attribution of examples. There's a couple resources here on just some of the actual technical background of the locality-sensitive hashing. And then that last one is the exact, it's the source code, it's of the custom processors, it's the flow, it's the configuration files, so everything that you need to get up and running on your own instances. And these slides will also be available. I'll put them up on, they're already on GitHub. I'm sure DWS will link to them. So if anybody doesn't want to type in URLs, you should be able to click on it pretty soon. Thanks very much. Any other questions? We still have a few minutes, so. Yeah.
You mentioned building your flows, your templates kind of backwards company.
Yeah.
It's a neat idea. Do you have obviously it depends on a rough idea of what kind of savings or headaches based on your own experience?
I have experience with a lot of headaches. I don't have any like numbers on what performance but like how much time that would save in building. But I can say that especially in, like I get called in for customer cases and we have this source system and we have this destination system and we're trying to rebuild the ETL pipeline that we have in a legacy system. I understand why that's your first instinct. It doesn't necessarily mean it's the best because, and this kind of goes back to that elephant picture as well. That's the only experience you have, that's the only data you know, so we're going to try and replicate that. You might be doing that to rebuild a system that is completely obsolete and unnecessary, and we have 18 shell scripts that all have to run sequentially, and it goes from A to B, but NiFi can do that with one processor. Like, it's Avro to Orc, it's not, the end of the world. So I would say starting at the end and remembering, knowing what your input, your original source is, but not treating that as equal to the destination helps because you can focus on what's important. The important thing is I get to the point where I need, this flow or this flow segment to end. I need the data in this location, in this format, maybe within this SLA or time frame. And then certainly the documentation is helpful, but I'll fully admit, it's reference documentation, it's not prescriptive documentation. If you want, here's how to build a flow to do this, the blogs and the mailing list and Stack Overflow and Hortonworks Community Connection and Twitter are the best solutions for that. If you want, I have update attribute processor and I need to know specifically what does this property do and when does it get triggered, then the reference documentation is excellent for that. There's an effort underway to make documentation more helpful for people who are not NiFi experts, but it's underway. It's not complete. So again, start from the end, know where you want to get to, use the documentation to see what options you have available at each step. But I have had examples where people go, it was a bank in Europe, and we're sitting in a meeting, and over the course of an hour, the guy explains they have 3 people, full-time staff, whose job is only to support this large shell script that somebody wrote 20 years ago, doesn't work there anymore. This is critical to their application. Without it, the bank doesn't work. We mocked up the same thing in NiFi with 3 processors during that hour. They didn't fire the people, but they moved them on to other stuff. They didn't have to keep paying them to do nothing anymore. There will be times where it just clicks and you go, I need to convert Avro to Orc, and you start typing that in and it's like, NiFi processor, convert Avro to Orc. And you're like, okay, well, that's pretty simple. There are other times where it's not that easy and you will have to do some manipulation and transformation. And there will be times where you're getting the data from is more important. There are times where you have some feed system that's not changing. That's the crown jewel of the company, or that's whoever's VP is over there is higher than your VP, and that's not going to change. So then you might have to start with the beginning and move out. in general, I'd say more than 50% of the time, it's easier to start with the end and go backward. Yeah. Anybody else? I'll give you a few minutes back. I think you have a break now anyway, so you're good. Thanks very much.